Hi viewers, welcome to the lecture series on frequency domain analysis in control systems. This is going to be the first lecture in this series. The objective of this lecture is to make the viewer understand what is meant by frequency domain analysis. As I start this lecture, I assume that the viewer is familiar with the basics of modeling of systems in frequency domain or in Laplace domain or S domain, or the viewer can model a system as a transfer function, and I assume that the viewer is familiar with the basics of time domain analysis. With this, let us enter into the topic.
LTI system. LTI means linear time invariant system. The system with an input R of t and output C of t. Both input and output are the functions of time. So for the known input R of t, if I'm interested to find out the output C of t, then the usual procedure we follow in time domain analysis is the entire system along with the signals will be transformed to Laplace domain or S domain. So if I transform R of t to S domain, I get R of S and C of t to C of S. The system will be transformed, the system dynamic equation, that is the differential equation written for the LTI system, will be transformed to Laplace domain, and that will result in a transfer function model. The transfer function of the system is represented by G of S. So therefore this R of S, C of S and G of S together forms the system model in Laplace domain. So here the advantage of Laplace transform is this output C of S can be written as a product of G of S and R of S. It is simply an algebraic multiplication. So therefore, if I'm interested to find out this C of t, only thing what I need to do is take an inverse Laplace transform on G of S R of S. Okay, inverse Laplace transform. If I take on this particular quantity, I will get C of t. This is what we do usually in time domain analysis. Though the system in real time is subjected to any arbitrary input, we test the system for a particular inputs. See, this R of t can be any arbitrary input, but when it comes to testing the system, we do it with a few standard test signals. So you should be aware of these test signals: the impulse signal, the step signal, the ramp signal, and the parabolic signals. So in time domain analysis, we take this R of t as any one of these signal and test the system. So when we test the system with these inputs, we get the impulse response if it is tested with the impulse input, step response if it is tested with the step input, and ramp response if it is tested with the ramp signal, and so on. Usually in time domain analysis, we do both transient analysis as well as steady state analysis. Otherwise, we say that the total response will have a transient part as well as a steady state part. So the transient analysis or the transient response is obtained by the inverse Laplace transform of this G of S or of S, whereas the steady state response is obtained by applying the final value theorem. Okay. So this is how we go in time domain analysis. However, apart from these set of standard test signals, we have another class of test signals, that is sinusoidal signal. So this sinusoidal signal is shown in this figure, and any sinusoidal signal is characterized by two quantities, two parameters. One is A, the amplitude, and the other one is the frequency. Okay, the number of oscillations or number of cycles in 1 second, this can be represented either in hertz, cycles per second, or in radians per second. So mathematically, a sinusoidal test signal can be represented by R of t is equal to A sine omega t. Please note that As a standard test signal, we assume that the test signal starts from 0, that is, the phase angle for this sinusoidal signal is 0. That is why we represent it as A sine omega t. Otherwise, it may have another angle such as sine omega t phi or theta or something. Also, please note that even though we represent the sinusoidal signal by A sine omega t, it can be represented by A cos omega t also, because cosinusoidal signal is nothing but a sinusoidal signal shifted by 90 degree. So, this sinusoidal test signals are very important signals in analysis of any system, because most of the time, most of the systems are applied with these sinusoidal inputs. For example, if you take any electrical or electronic or communication circuit, most of these systems will have the sinusoidal voltages or currents as their inputs. Apart from this, even the mechanical systems, there are mechanical systems which will have periodic inputs as its input, periodic signals as inputs. You might have studied in Fourier transform or Fourier series that any periodic input can be expressed as a sum of sinusoidal signals. Therefore, even if I want to analyze a mechanical system or an electromechanical system for any periodic signal other than sinusoidal signal, I can resolve those periodic signals into sinusoidal signals, and I can give those sinusoidal signal as the input to the system and analyze the system. Therefore, sinusoidal signals are very important signals to test the performance of any system. Even for these sinusoidal signals, we can do the transient analysis, or we can get the transient response as we do for these other standard test signals, like by getting this inverse Laplace transform of G of s and R of s. However, there is a problem in the steady state analysis. How do we do the steady state analysis for these inputs? We apply the final value theorem. The condition for applying the final value theorem is that the signal should settle at some value as t tends to infinity. The value at which it is going to settle may be finite or infinite, it doesn't matter, but it has to settle at some value. But if you take any sinusoidal signal, that doesn't happen. Even after settling, even when t tends to infinity, this sinusoidal signal oscillates. Its value changes from one value to another, but within some bounds. Okay. So it doesn't reach a steady state value. It doesn't reach a steady state value. Therefore, you cannot apply the final value theorem. So that's the problem with this sinusoidal signal. So therefore, this steady state response for a sinusoidal input has to be analyzed separately. This is what we do in frequency domain analysis. Therefore, two things the viewer has to understand is frequency domain analysis is an extension of time domain analysis. That's the point number one. And the second thing is frequency domain analysis is a steady state analysis. Basically, we are not interested in transient analysis with the sinusoidal signals. Of course, it doesn't mean that we are not interested in the transient analysis for sinusoidal signals. The transient analysis for the sinusoidal signals can also be done as in the same way we do for other standard test signals, but steady state analysis we cannot do as we do for the other test signals. So we do the steady state analysis for the sinusoidal signals separately. So that particular study we call as the frequency domain analysis. Anyhow, we will see what is meant by frequency domain analysis in detail as we progress in this lecture. Therefore, let us analyze a system with this sinusoidal signal for its steady state response. Let us say the input for the system is r of t equal to a sine omega t. We know the Laplace transform of our sinusoidal signal is sine omega t is omega by s square plus omega square. Since a is a constant, it is left out as it is. As we do in the time domain analysis, our objective is to find out the response in time domain, but we are interested in the steady state response. Anyhow, let us proceed as we proceed in time domain analysis. What do we do in time domain analysis? We take g of s and we multiply g of s with r of s, and that gives my c of s. So let me do the same thing here also. So g of s, r of s is a into omega by s square plus omega square substituted. So this x square plus omega square can be written as x square minus j omega the whole square, because j square is minus 1. So you will get this. The purpose is just to factorize this s square plus omega square. So now I can apply a square minus b square formula. A square minus b square is equal to a plus b into a minus b. So therefore the denominator becomes s plus j omega into s minus j omega. Okay. And of course, g of s will also have its own numerator polynomial and denominator polynomial. So g of s represents that particular transfer function, that is a rational, it is going to be a rational function. So to find out the inverse Laplace transform, what we need to do is we need to split this function into partial fractions. Let us do that. So if you look at this function, you will have factors corresponding to this input, that is s plus j omega and s minus j omega obtained from this Laplace transform of input. And also, as I said, g of s also will have the denominator polynomial and numerator polynomial. Therefore, there will be some partial fraction terms related or associated with this g of s. Okay, so these are simple factors, s plus j omega and s minus j omega are simple factors, and therefore they can be resolved into partial fraction like this. And as I said, again, g of s also will have some partial fraction terms. If you look at carefully, this s plus j omega and s minus j omega has originated from this input. Okay, so therefore these are due to the poles of input r of s, and so these terms will correspond to the poles. These partial fraction terms will correspond to the poles of the transfer function g of s. If we are interested only in the steady state response, or if we are not interested in the transient response, the partial fraction terms corresponding to g of s can be neglected or omitted. If you don't understand this, let me explain this with an example. Let us take a first order system. G of s here is k by ts plus 1, where t is the time constant of the system. And let me say that the system is applied with an unit step input. So the Laplace transform of unit step input r of s is equal to 1 by s. So this is my g of s and this is my r of s. And obviously c of s, the output, will be the product of g of s into r of s. So this is the product. So to find out c of t, the solution in time domain, I should again do a partial fraction for this. So if I do a partial fraction, I'll be getting this. You can try this. This is what I'll be getting if I do a partial fraction on this. So I get two terms, one term corresponding to s and another term corresponding to ts plus 1, or I can write it as s plus 1 by t. So if you notice, this s originated from this input. So this is due to the pole from the input, whereas this particular term originated from G of s. It originated from G of s, the system, pole from G of s. That is very clear. So since we have got C of s as partial fraction, definitely I can get the C of t, that is the output, by taking the inverse Laplace transform. K by s will have an inverse Laplace transform as Ku of t, and K by s plus 1 by t will have an inverse Laplace transform of K into e power 1 by t into t, or minus t by t, small t by capital T into u of t. See, obviously this exponential, this term which has got this exponential term is going to be the transient part of the response, and this is the steady state part of the response. So if you clearly relate this to the C of s, the partial fractions, this steady state response is associated with the pole from the input, whereas the transient response is associated with the pole from G of s. Clear? So therefore, if I am interested only in the steady state response, not interested in the transient response, I need not take this particular term. Otherwise, the partial fraction term corresponding to the poles from G of s. This particular structure will be exhibited even in second order system. You can try that. So therefore, the conclusion is, if I am interested only in the steady state response, not in the transient response, then all the partial fraction terms originating from G of s can be neglected or omitted. So for our analysis, as I said, our analysis is going to be only the steady state analysis, and therefore I need to consider, or we need to consider, only this particular part, and this particular part, let me call it as C double S of S. Now, if I take these two terms now, if I want to find out C of t, then obviously I should find the residues K and K conjugate. Please note that the steady state response in time domain is CSS of t, which is nothing but the inverse Laplace transform of CSS of S. Also, for any factors whose roots are complex conjugate in nature, the residues also will be complex conjugate in nature. Here, the roots of this denominator will be plus or minus j omega, which are complex conjugate. Therefore, k and k conjugate will appear as the residues. So, if I want to find out C of t, otherwise CSS of t, it is necessary to find out this residues constants k and k conjugate. These are simple factors, and therefore there is not much difficulty. So this is what is expressed as this. So if I want to find out the residue corresponding to S plus j omega, then I should take the entire function except this x plus j omega, but I should substitute S is equal to S minus j omega. So that is what I get here. K is equal to A omega g of s by s minus j omega. The entire thing calculated at s is equal to minus j omega. So let us substitute s is equal to minus j omega. What we will have is a omega g of minus j omega, and s is equal to minus j omega. We get minus 2 j omega in the numerator, as it is a omega g of minus j omega. Please note that g of minus j omega is going to be a complex number, and therefore I can write it in polar form, the magnitude and the angle. So r e power j theta form. Okay, so I can write in this way. So in the same way, we can find out the residue k conjugate also. Only thing is, I have to take the entire function except s minus j omega, but I have to substitute s is equal to j omega there. And if I do the similar substitutions, this is what I will get. So I got k and k conjugate. So since I have got the residues, I can take this CSS of S, only this part of C of S. I am writing it here, and K conjugate, whatever we are substituting them here. So now, since C of S in terms of partial fractions have been obtained, I can find out CSS of t, that is the steady state response in time domain. So if I do that, this is a constant that will appear as it is, and 1 by s plus j omega will result in e power minus j omega t. Please note that the inverse Laplace transform of 1 by s plus a is equal to e power minus at. So here a is j omega and therefore e power minus j omega t. Similarly, this is also a constant that will come as it is, and the inverse Laplace transform of 1 by s minus j omega t is e power j omega t. So this expression can be further simplified, because for any real valued signal, g of minus j omega is equal to conjugate of g of j omega. The magnitude of g of minus j omega is going to be equal to the magnitude of g of j omega, and angle is going to be negative. Okay, so angle of g of minus j omega is going to be minus angle of g of j omega. So if you make these substitutions in the above expression, this is what it becomes. G of minus j omega magnitude is same as g of j omega magnitude, and this angle I can replace with a negative sign here. So g of j omega. So obviously A appears as a common term, and the magnitude of g of j omega also appears as a common term, and they can be taken out, and here I get e power j something. Please note here, this minus j omega t and this j angle of g of minus j omega can be combined. That is what is being done after putting this substitution. So they have been combined and they get a single exponential term. So this is what you get. So you can notice that this angle and this angle are negative to each other. Please notice that e power j theta, there should be a j coming here, e power j theta minus e power minus j theta divided by 2j is equal to sine theta. So therefore, this also can be written as sine omega t plus angle of g of j omega. Okay, and here it is a into g of j omega. So this is what is the final result. This is what is the final steady state response of the system with a sinusoidal input. The entire result can be represented in a block diagram like this. If I give an input, sinusoidal input a sine omega t, to an LTA system with a transfer function g of s, this is what the output I'll be getting. What is the frequency of the input? It is omega. What is the frequency of the output? That is also omega. So the important point to be noted here is the frequency of the output will be the same as the frequency of the input. However, there are two changes in the output. One change is in the amplitude. See, the amplitude of the input is A, whereas the amplitude of the output is A into magnitude of G of j omega. So that means the amplitude or the magnitude of the input is multiplied by g of j omega's magnitude. And similarly, there is a change in the phase also. The original phase was 0. Yes, we took it as a sine omega t with a phase angle of 0. But whereas the output will have a phase difference, phase angle, phase lag or lead, which is nothing but it is given by angle of g of j omega. So let us illustrate this. Let us further explain this with the help of an example. Let us take a first order system. So that is the simplest dynamic system we can consider. So let us say the transfer function of the system is 1 by s plus 1. So how do I get g of j omega? If this is g of s, to get g of j omega, simply substitute s is equal to j omega. So if I replace all the s by j omega, this is what I'll be getting. If you look at this, for a particular value of omega, this g of j omega is going to be a complex number. For example, let us say omega is equal to 1. Then this is going to be 1 by 1 plus j. So this will ultimately get reduced to a complex number. So therefore, another important point you should understand is g of j omega is always a complex number. Please note that any complex number will have a real part and imaginary part if they are represented in rectangular coordinates, rectangular form, or they can be represented in polar form also. So otherwise we can say that these complex numbers will have a magnitude and an angle when they are represented in a complex plane. So the complex numbers or g of j omega can be represented either as real part and imaginary part, or it can be represented in polar form with its magnitude in and angle. So if I write it in polar form, the magnitude is going to be 1 by root of omega square plus 1, because if I have a complex number z represented by a plus jb, then its magnitude is given by root of a square plus b square, where a is the real part and b is the imaginary part. So that is how I get the numerator magnitude is 1 and the denominator magnitude is root of a square plus b square is omega square plus 1. What about its angle? If z, a complex number, z is represented by a plus jb, then its angle is given by tan inverse of b by a. So if you take the numerator 1, it is a is equal to 1 and b is equal to 0. That is tan inverse of 0 by 1, that is tan inverse of 1, sorry, tan inverse of 0, tan inverse of 0 is 0. So therefore, the angle contribution from the numerator is 0, whereas the angle contribution from the denominator is tan inverse of omega by 1, b by a, imaginary part is b, that is omega. Okay, so tan inverse of omega by 1, that is tan inverse of omega. Since this is a division of two complex numbers, the net angle will be 0 minus tan inverse of omega, that is nothing but minus tan inverse of omega. That is how we get this polar form, the magnitude and angle. Please note that this g of j omega is a function of omega. Therefore, the complex value will be different for different frequencies. Therefore, the magnitude and the angle of g of j omega will be different for different frequencies. Okay. So therefore, if I have a system like this is g of j omega. G of j omega is written by its function, and I give an input, sinusoidal input. The output is a into magnitude of g of j omega into sine omega t2 phi. please note that for a particular frequency, if g of j omega is 1, then what will be the magnitude of the output? A into 1 will be A, same as the input. But for another frequency, if g of j omega is lesser than 1, what will be the value of this magnitude together? A into a value lesser than 1 will be something lesser than A, and therefore the amplitude also will be less. If magnitude of j omega is greater than 1, what will happen? The total amplitude will be greater than A. Okay, so I may not get the same amplitude at the output. Either I will get an increased amplitude or a decreased amplitude depending on the value of g of j omega magnitude at that particular frequency, at that particular omega value. And similarly, this phase angle also will be varying with respect to omega because it is minus tan inverse of omega for this example case. The phase can be leading or lagging depending upon its value. Maybe to illustrate this, I will take up a small simulation. So the simulation is done in XCOS. It is a MATLAB Simulink equivalent available in Scilab. So this is the system, and input is given, a sinusoidal input is given, and the output is taken from the system. Both the output and the input are given to a scope through a mux. So let me define my input. The amplitude I have taken is 10, whereas the frequency, let me start from a smaller value, 0.2. So if I take this frequency, let me simulate it. So this is what the output. The black one shows the input and the green one shows the output. So you'll be able to notice that the output magnitude is almost same as the input magnitude, but whereas there is a small phase delay in the output. Okay, that's what you observe. So now let me increase the frequency from 0.2 to 0.5. This is this waveform, input waveform, and the green one is the output waveform again. And the output simply follows the input. So therefore, the frequency is going to be the same as the input, whereas the amplitude has slightly reduced and the phase has slightly increased. Okay, yeah, you notice this. Let me increase the uh, frequency further. Let me make it as 1. Again, the output follows the input, so therefore the frequency is same, whereas the output magnitude decreased and the phase also slightly increased further. So let me increase the frequency further. Let me say this frequency is 5. Okay, the output follows the input. However, the magnitude is reduced drastically and the phase angle also increased. Let me increase the frequency further. Let me say 50. Interesting, there is no output. Output is very, very, very little. Output is very, very little. So it's very clear that the steady state output of a LTA system varies with respect to its frequency because the amplitude is A into G of j omega, otherwise the amplitude is decided by G of j omega, and the angle is also decided by angle of G of j omega. So what we can conclude is the steady state response of an LTI system for a sinusoidal input merely depends on G of j omega. So if I want to analyze the performance of an LTI system for a sinusoidal input, it is simply sufficient to analyze the variation of G of j omega with respect to omega. That is the conclusion that we can get from all these discussion. So therefore, it will be a good idea to plot the variation of g of j omega and the magnitude of g of j omega and angle of g of j omega with respect to frequency. So the first plot, I'm going to call it as the magnitude plot because the magnitude plotted versus frequency. And the second plot, I will call it as the phase plot because the phase of g of j omega is plotted with respect to frequency. By looking at this frequency magnitude plot, I can say that for frequencies greater than 20 radians per second, the gain contributed by the system g of j omega is very small, and therefore even if I give a larger signal, the output is going to be very small. That's what is the inference. So for smaller frequencies, for low range frequencies, the gain is almost close to 1. So that is what we understand. And from the phase plot also what I understand is if I increase the frequency from lower range to higher range, the phase contribution, it is negative. Please see that it is negative. So the output will be lagging by 20 degree at this particular frequency and 40 degree at this frequency and 80 degree at this frequency. And if I increase the frequency beyond 20 radians per second, then the phase lag is going to remain constant at almost 90 degree. So I understand the performance of the system for different input frequencies, both through this magnitude plot and the phase plot. These kinds of plots, okay, the plot of g of j omega with respect to frequency is what we call as the frequency response of the system. And any analysis done through this frequency response is what we call it as the frequency domain analysis. So these are the frequency domain plots, and any analysis done with them or what we call it as the frequency domain analysis. So now let us conclude the lecture. So we understood that frequency domain analysis and an extension of time domain analysis concerned only with the steady state response. And for a sinusoidal input, A sin omega t, the output is going to be this. There is a change. There is no change in the frequency. Only the amplitude and phase angles change with respect to the frequency. The input amplitude is multiplied by a gain of magnitude of g of j omega, whereas a phase of this much is added to this input. That is what is the changes. The two changes will be happening from the input to the output. Therefore, output of an LTI system for a sinusoidal input of a particular frequency depends on the gain g of j omega and phase of the system at that frequency. And also, to understand the system performance, it is just sufficient to plot to understand how these quantities g of j omega magnitude and phase varies with respect to frequency. Those plots are what we call it as frequency domain plots, and any analysis done with these frequency domain plots are known as the frequency domain is known as the frequency domain analysis. So with this, we wind up this lecture, and in the coming next lecture, we will see what are the different ways in which I can represent this variation of g of j omega with respect to frequency, or we'll see the different types of frequency domain plots and a few specifications associated with this frequency domain plots. Thank you.